cases where the blocks, they are moving purely along the y-axis. That is vertically, their motion is constrained in the vertical direction. Over here we have a pulley. The pulley is massless, it is frictionless, there is no friction at the axle. So there is no force or any torque, etc., which is being used over here at the axle. So this is frictionless pulley, this is massless pulley. The strings, they are massless, this string is massless, and the string which is connecting 20 kg block and 5 kg block and passing over the pulley, this is also massless. All the things, they are ideal. We are asked to find the tension in these strings, this string and this string. This is obviously one string. Whatsoever tension is over here, the same tension is going to be over here. One string, one tension in the ideal string. So now over here we observe that is these motions, they are purely along the y-axis. There is no force along the x-axis. What we do is we draw a force diagram. Once again we draw a circle. Elementary thing first we do, and then we see that is how fast we can do it without drawing the force diagram for each block. So over here we know that this will be going down. This will be going down with the acceleration A, and this will be going with the acceleration A. Obviously the string is inextensible. So if you pull it by 1 meter, this will go by 1 meter. If you pull it by 10 meter, this will also go by 10 meter. It is not possible that this goes by 5 meter and this goes by some other length, right? So whatsoever is the velocity of this block downward, the same velocity will be of this block upwards. Whatsoever is the acceleration of this block downwards, the same acceleration will be of this block in the upward direction. So we have isolated the bodies by drawing the circle. So the first step of free body diagram is done. That is isolate the bodies diagrammatically. Then is draw forces. Let's draw forces. Earth says I'm going to pull you down with a force of mg. G we are taking as once again 10 meter per second square. So m into g, that is 20 into 10, that is 200 Newton. Onto this 5 into g, that is 5 into 10, that is 50 Newton. Apart from this, the tension in this is going to be in this direction away from the free body, and tension is outward for this away from the free body. Now we can write the equations as we are writing, that is we are using now last step our force diagram, free body diagram method, that is we have to apply resultant force equal to mass into acceleration. We apply this individually to both the blocks. For this block, when we talk about this block, the equation is going to be, it is going down, so this force is greater than this force. So equation is going to be 200 minus T net force. So net force is downward forces minus upward forces because this is accelerating downwards. If this is accelerating downwards, so obviously the net force has to be in the downward direction. What we shall be doing is, we shall be subtracting from downward forces, upward forces will be subtracted. So it is 200 minus T is the net force is equal to mass. Mass is 20. Acceleration we don't know. So this is the first equation. And for this, it comes out to be, when this goes down, this will go up. When this accelerates down, this will accelerate up. So this force should be greater than this force. So equation for this is T minus 50, that stands for net force, is equal to 5 into acceleration. If we add the two, minus T and plus T will get cancelled. So 200 minus 50 is the 150, 20A plus 5A, that is 25A. So A comes out to be 6 meter per second square. If A comes out to be 6 meter per second square, we can put it in any equation. Out of these two, we can put A is equal to 6 meter per second square and we can get the answer. Let's say we put it over here. So T is equal to, so T minus 50 is equal to 5 into 6. So T is equal to, we get the answer as 80 Newton. Is there any shorter way that is to get the same answer? We can get the same answer quickly if we consider, let's say, what is happening which if we take these two bodies as one free body. So over here the force is mg 200 Newton. So this way is 50 Newton. All the forces along the y-axis. This is one string. This is like kind of a tug of war that is over here. This end is being pulled with 200 Newton and this team is pulling it down with a force of 50 Newton. So along the string, the net force is 200 minus 50. Then net force is in this direction. So net force along the string is 200 minus 50 is the net force is equal to mass. This resultant force, this net force is responsible for accelerating both the blocks. So it is not just 20 kg or 5 kg, but net force, we have taken the force, we have taken the net force, we have taken the net force on this whole system of these two blocks. So the mass of both of them, that should be taken into consideration. 20 plus 5, that is 25 into A. So this comes out to 150 by 25 is equal to A. So A comes out to be 6 meter per second square. So this comes out to be 6 meter per second square. You get the same answer. Now if you have to find the tension, so now you can do it. This is T. Equation for this will go up. So it is T minus 50 is equal to mass 5 into acceleration. What is the acceleration? We have got it. We have got the acceleration as 6 meter per second square into 6. T comes out to be once again 80 Newton. One thing that is what you should definitely remember is what is the relationship between the tension in this string and tension in these strings. A very, very important point. So what we do is, because this is a different string, these are different strings. So what we do is we draw a circle onto it. We draw a circle onto it, so that there is no confusion, that is we don't get confused by rest of the matter. So what we do is I erase all this rest of the matter, I erase. So what is left is something like this. When all the rest of the things they are erased from the board. The circle was drawn as a free body to isolate this body. Now we know that its tension is outward. So this is T this way, T is this way, there's one string only. And over here that is once again tension is outward, so this is T dash. The thing to be noted is that is the pulley is massless. The pulley is massless, it doesn't have a mass. And this is hanging from a fixed support. So it means that this pulley is neither going up nor coming down. So it means summation of forces is equal to 0 along the y-axis. That is net force along the y-axis is equal to 0. That is, it is not moving in the upward direction or downward direction. So it means the upward forces they have to equal to downward forces. Upward forces T dash, downward forces they are 2. Now T is here, T is here. So this is going to be 2T. So T dash is equal to 2T is a result which shall be extensively used in time to come. Now let's take an example which more or less is like what we have done earlier. So over here what we have is, we have a 10 kg block, we have a 10 kg block, we have 5 kg block. So the number of strings we see over here is, one is this string, massless idle string. From here to here, massless idle string. From here to here, this is a third massless idle string. So I have 1, 2, 3 strings over here. Let us say we are asked what is the tension in this string. So what we can directly do is, that is we can say that this side, what is the acceleration? Now let's look at the acceleration first. Instead of going individually to each block, now let's find out acceleration in a faster manner. Even if these two blocks, they are combined together and made as 20 kg a single block, there will not be any alteration in the acceleration of this system. So this side, whole side is being pulled down by earth with the force 10 plus 10, 20 kg, 20 into 10, that is 200 Newton. And this side is being pulled with the force mg, that is 50 Newton. So along the string, the net force is 200 minus 50. That is what we have done in the earlier example also. So net force is 200 minus 50. Net force is equal to total mass 25 into A. So A comes out to be 6 meter per second square. If we have to find the tension in this string, so simply draw the force diagram for this. When you draw the force diagram of this, please understand that is now you will not take 200 Newton into consideration. You are drawing the force diagram of this, so you will just bother what are the forces acting on it. 200 Newton was good enough when we had to find the acceleration of the system. We have just found the resultant force. This way it is 20 kg heavier, that is 20 into 10, that is 200 Newton this way, 50 Newton this way. From there we get the net force, 200 minus 50 net force is equal to total mass into acceleration. We have got the acceleration. But if we are considering this block, we shall be considering all the forces which are acting purely on this block. If we are considering this block, we shall be purely talking about the forces which are acting on this block. Though we can use the result of acceleration which we have found by this shorter method. So equation for this is going to be 100 minus T is equal to 10 into acceleration. Acceleration is 6. So T is equal to 100 minus 60 is equal to 40 Newton. One of the mistakes generally the students do is when they make a free body diagram of this. So what they do is, that is, suppose this is T1. They will say T1 is here, T2 is here, and they try to make equation, this is coming down, that is T1 minus T2 is the net force is equal to mass into acceleration. This is wrong because over here you have missed one force, that is 100 Newton, that has also been taken into consideration. So right equation for this is, this is acceleration down, so downward force is T1 plus 100. T1 is tension. These strings, tension in the strings, T1 plus 100 is the downward force, minus T2 is equal to mass. Mass is 10 into acceleration. Acceleration is, we have got 6. So from here we can get what's the value we have to find. So we have considered the examples where the motion of the blocks, it was purely along the x-axis or purely along the y-axis. Is it possible that some blocks they are moving purely along the x-axis and other blocks they are moving purely along the y-axis? Let's see.